Welcome folks to this video on vector calculus in which we describe the cross product. So the cross product is the second of our vector products. We'll see it has some similarities and some differences to the dot product that we talked about last time. So we'll start again with the definition. We'll talk about some properties of the dot product or the cross product, and then we'll finish with an application too. Okay, so here is the definition. The definition of the cross product is given in terms of those special unit vectors from before, I, j, and k, in terms of a 3x3 determinant. Now, some of us have seen this type of determinant before. A 3x3 determinant is defined in terms of three 2x2 determinants. So let me just write down quickly what a 2x2 determinant is. So a 2x2 determinant, A, B, C, D, is computed by multiplying A times D and subtracting B times C. So here we see how the cross product is a combination of those 2x2 determinants. And here are those three 2x2 determinants. So it's U2, U3, V2, V3 in the I direction, minus U1, U3, V1, V3 in the J direction, plus U1, U2, V1, V2 in the K direction. Okay, so here's an example of a cross product. Go ahead and write this out in all of its detail, and then we'll see how we find a vector value out of this cross product. So here we see that I've written the 3x3 determinant in terms of these three 2x2 determinants, and what's left is just to crank out those determinant values in the I, j, and k directions. In this case, it turns out we get 13i hat plus 13j hat plus 13k hat, which of course we can use our vector notation to write also as 13 comma 13 comma 13. Okay, so there's a cross product, again, just a 3x3 determinant, which is three 2x2 determinants. Okay, a few properties of the cross product. Here are some properties based on that definition. The first property is a commutative-like property. It says that V cross U is negative U cross V. The second is that the cross product of a vector with itself is 0. And the third is that the cross product of U and V is perpendicular to both U and V. Okay, so again, the first two of these properties come back to looking at the definition. And the third property, actually, we know from last time that we can show something is perpendicular by looking at the dot product of the thing, the two things that we want. Okay, so again, the first two properties are verified with the definition. And the third is just showing that U dotted with U cross V is 0, as well as V dotted with U cross V. And it's kind of a tedious but a pretty quick calculation to figure out. Okay, there's a geometric interpretation of the cross product too, and it turns out that the cross product is related to the sine of the angle between the vectors, and the way that one shows this is just by multiplying out all of these components and showing that what you get in the magnitude is exactly what you expect to get. Okay, so algebraically this derivation is a little bit of a mess, but the way one does it is by multiplying out the magnitude of U cross V squared, showing that what you get after a lot of algebra and factoring is magnitude of U squared times the magnitude of V squared minus U dot V quantity squared. Now, of course, we can use the geometric interpretation of the dot product here on U dot V quantity squared to substitute that in terms of U, V, and the cosine of the angle between. So this, as it turns out, can be written as magnitude U squared times magnitude V squared times the quantity, 1 minus cosine squared, So of course 1 minus cosine squared is just sine squared, and we're given then the identity that we want. Okay, so again, the geometric interpretation of the cross product is that the cross product of two vectors in magnitude is related to the sine of the angle between them. Okay, so a couple applications of this. Here's the first one. The first one is that we can use the cross product to find a vector that's orthogonal to a plane through 2 points. So here we'll do this by thinking of one of the vectors in the plane connecting P and Q, and another vector in the plane connecting P and R, and then of course the cross product of those two vectors gives us back exactly a vector that's orthogonal to the plane. So again, here we've taken U to be the vector connecting the point P to Q, so -3, 1, 2. We've taken V to be the vector connecting P to R, so 3, 2, 4. A vector perpendicular to both U and V, those are both in the plane, is given by U cross V. So we'll just crank out U cross V, and that's a vector that's orthogonal to this plane. So again, just do all the computation there to crank out this cross product, and you should get 0, 18, minus 9, and that turns out to be a vector that's, again, orthogonal to this plane. And it turns out you could have used a different combination too. You could have used PQ and QR or something like that, so I'll challenge you to show that you get a vector perpendicular in those cases too. Okay, one final application here is that we can use the cross product to find the area of a triangle formed by two vectors. So again, the way we do this is through a little bit of trigonometry and the geometric interpretation of the cross product in terms of the sine of the angle between the two vectors. So here I've stylized this triangle formed by U and V by trying to connect the ends U and V to make a triangle here, and then thinking about the height of that triangle, which ends up being related to the opposite side and the hypotenuse of the angle between the two. So since the height is given by the opposite side, of course that height is related to the sine of the angle theta, and the base of the triangle, of course, is related to the magnitude of V. Okay, so of course the base is the magnitude of V, the height is the magnitude of U, the area of the triangle is 1/2 base times height, so 1/2 magnitude U, magnitude V sine theta, which of course is exactly 1/2 times the cross product of U with V. So if you form a triangle given two vectors U and V, the area of that triangle is 1/2 times the cross product, times the magnitude of the cross product of U and V. Okay, thanks for your attention, folks. Hope you've enjoyed this video on the cross product, and we'll see you next time. Bye-bye.